very good morning, good afternoon, good evening, my dear friends. Welcome back to the TQM, which is Total Quality Management course, which under the NPTEL program. And as you must now have got used to my name, I am Raghunandan Sengupta from the IME department, IIT Kanpur. So this is the 16th lecture, technically, which would be, if we follow the principle of 5 lectures per week, so it would be the starting of the 4th week. So as we remember, we were discussing about the producer's risk and the consumer risk. Now to give to illustrate the background in more details, I have done that, but I'll still like to dwell on that fact much more. Is that whenever you are supplying any product, whether you are giving a services, trying to basically supply a motor, trying to supply a car, sell some product, whatever it is, they would be basically, and obviously there are some inspections to be done for those products, the quality assurance criterias and those norms have to be met. They can be two level of risk or two different type of risk. So this risk is basically from two different levels. Levels means two different players. One is basically who is the supplier of that good or that product or the service, and one is basically the person who is buying it. So obviously one risk, or if risk I am using the word to make it very simple, is some sort of loss or some sort of negative impact it has depending on the outcome. So if it is a risk for one, obviously it will be on the other side, it will be a positive one for the other player, which is, if it is risk for the for the supplier, it would be the positive one for the buyer, and vice versa. So one would be the consumer risk, one is the producer risk. Technically the words are what we mean by the concept of alpha and beta. If you go back to the basic concept of hypothesis testing, it will be, you are making some product that has some problem but still is being accepted, which would be some positive part on your gain, on your part, but it would definitely be a risk for the other person who is buying it. Now if the scenario is turned in the sense, good items are there but they are being rejected, which means that you are facing a problem, you have a risk, the other person has a positive part. So basically this is the overall thing which we would be analyzing time and again, depending on the distribution, depending on total sample size, depending on what is the total acceptance level, and also depending on what is the total population size. Now technically population size should be infinite, but for the hypergeometric and such distributions where quality concepts are there, capital N would also come into the picture. Obviously capital N is very large with respect to small n, but still it will come into the picture, such that capital N, small n and C are, apart from alpha and beta, which is the producer risk and the consumer risk, would dictate how the graph looks like. So to give you an example as per the concept of acceptor sampling, now again I will again step back. Acceptor sampling, when you are saying that, it means that you are picking up some chunk and you are making a decision whether to accept or reject that actual lot. Now picking up a set of observations can happen in many ways. So as if you remember in the last lecture, we did mention a word known as sequential analysis or sequential sampling, or the double level of sampling, and so on and so forth. So technically means that you pick up set of observations, make a decision based on what the outcome is. Either you proceed for the second step or try to take another set of observations, or basically reject that actual sample, or also accept the sample depending on the C, that means the ratio of C by N would be the relative frequency or the actual probability of such defects in a small sample, whether that is exactly equal to some stipulated value, whether it is more than that stipulated value, or whether that less than that stipulated value. Based on these three outcomes, you will take a decision. So these technicalities how you can make if and then concept, like if the number of defects are greater than equal to some number of C, or if they are less than C, or they are equal to C, how you make the decision would basically depend on your level of competence, level of accuracy, the cost structure, the sample size, the population size, what type of distribution you are considering, all this would come into the picture. Now, if you have the probabilities of acceptance for the single sampling plan as per tables 15.2, so let me mention this table has been taken from the Montgomery book, which you are trying to follow for our TQM1 course, as well it will be followed for our TQM2 course, which will be floated later on. So, probabilities of acceptance for the single sampling based on the fact that n, small n is 89 and C, which is the total number of defects which you can have, is 2. So, the overall fraction of defectives are given in the first column, and the probability of acceptance. Now, if you remember, when you are drawing the AQL curve, so you will basically have something measured along the x-axis and something measured along the y-axis. So, those informations, as already stated, one would be basically with the fraction or defect which is given by P, and another would be the probability of acceptance, which will be given by P suffix A. So, as the fractional defects are given, the probability of acceptance are given. So, obviously it means that as the fraction increases, then the probability of acceptance decreases. Obviously that would be true, because more defects you find, less would be the chance of accepting that particular set of observations of sample. Now, if you come to the graph which is being shown in this slide, so this obviously the graph looks simple, and obviously you will encounter such graphs later on also. What I want to mention is like this. Now, if you remember, let me make the color. So, if you pay attention to the y-axis, you are measuring basically the probability of acceptance, which is P suffix A. If you are paying attention to x-axis is the lot fraction defective. So, what you actually do is that depending on small n and C, you will have a particular graph. So, in case is a hypothetical thing which I am trying to draw. In case, say for example, you have this y-axis as PA, x-axis as PP, and you have different n's and c's. So, obviously your graphs, some would be like this, some may be, I am just drawing it in order to make you understand, depending on the distribution and capital N, small n and C, it will change. Some of the graphs may be like this, some of the graphs may be like this, and so on and so forth. So, all these graphs which you see would basically be depending on N, on C, and also on capital N, point 1, and it will also depend on the type of distribution which we are using. So, this would measure P and this would measure P suffix A. So, the specific points for in the operating characteristics curve. So, you will basically have again the LTPD and the AQL levels, which technically has some information of the alpha and beta. So, the OC curves would have the characteristics which are in general true are as follows. The poorest quality level for suppliers process that a consumer or a customer would consider to be acceptable as a process average is called the accepted quality level or the AQL level. AQL is a property of the supplier's manufacturing process, not a property of the sampling plan. So, generally if the sampling plan is, say for example, some capital N, some capital small n and some C. So, obviously it would depend. So, that would basically keep the curve fixed, but where you basically go to accept or reject a particular lot would depend on what is your manufacturing process as such. So, if you finally visualize, the curve remains fixed, but where you basically cut on the horizontal axis and the vertical axis of the values of P and PA would depend on how the manufacturing process is going on. Now, going to the second point, the protection obtained for individual lots of poor quality is established by the lot tolerance percentage defective, which is LTPD, also known as rejectable quality level, which is RQL, or the limiting quality level. So, obviously, it would mean that AQL and LTPD are some concepts which generally go hand in hand, that is true, but whether one increases and other decreases or vice versa, that has to be studied. And if you understand the overall concept of the producer's risk and the consumer risk, it will come out immediately to be true. That, as if you remember that as I started the class and when I was showing the 16th slide and when I began the class, I did mention the risk or the loss for one person is basically the positive gain for the other person. So, obviously, that will give you the information that how does the concept of AQL and LTPD behave, which will give you some good idea. So, LTPD is a level of lot quality specified by the consumer, not a characteristics of the sampling plan. Sampling plans can be designed to have specific performance at the AQL and the LTPD points depending on what the manufacturing process capability is. So, now with this graph, it will be much easier for me to explain, which I have been talking about time and again at the beginning of the class as well as the fag end of around about 10-15 minutes when we were completing the 15th lecture. Now, if you consider again the x axis and y axis, they are same. So, you have basically probability of acceptance lot, which is giving along the y axis, the lot quality, or which is the fraction defect is given along the x axis. And if you consider the graph given, so consider the graph given as specified depending on some value of capital N, some value of small n, some value of c, and consider the graph is given as it is. Now, let us consider the details of LTPD and AQL values in more detail. So, let me change the color to, say for example, red, so it will be easier. Now, depending on the manufacturing capability, you have basically specified some value of alpha, and depending on the other end of the depend on the consumer risk and producer risk, you have also specified some beta value. Now, what you want to do is that if you are between these two ranges, whether below or above would depend on which side of the story you are looking at, you will basically accept or reject that lot, and obviously that would have a positive or a negative consequence for the consumer and the producer. So, if it is basically loss for me, it is a gain for you. So, in this region where I am now hashing, these are all goods, good things. Goods is not the product. Good means in the characteristic sense is a good one. And all the things which are there on the right are basically bad. So, technically I would consider only this. I did draw the hashed lines above that also, but technically this is the area which is bad. Now, what you technically do is that depending on the N, C and capital N value, you basically have some lot quality fraction and defect or the probability acceptance, whatever is given. You go vertically up, find out the point and find out, say for example, what is the level of the probability of accepting that particular lot depending on the lot quality fraction of defects which are there. Now, if you consider on alpha and beta, again I am mentioning they are the risk from the producer and consumer, which technically means that if products are falling in this range onto the left or in this range, say for example, onto the right, so there may be chances that a good quality product is being rejected or a bad quality product is being accepted. So, that has to be basically understood in such a sequence that alpha and beta value would basically dictate to what level good and bad items would definitely be rejected or accepted depending on which side of the story you are looking at. So, to explain it further, again the same graph, but basically the actual example which is being given is not with the data, but I am only trying to specify the overall coverage areas of the different portions of the graph. As per the same norm, we are measuring probability of acceptance lot along the y axis, we are measuring the lot quality fraction defect along the x axis, and the curve which is shown here which is the black one, where I am hovering my pen now, I am not drawing it, is basically the quality characteristic curve. And another curve is, which is the red one, which is dotted, is shown like this. So there are two theoretical graphs which have been drawn. So actually they would depend on the values of capital N, small n, C, and the distributions which you have. So it mentions that OC curves come in various shapes depending on the sample size and the level of risk of alpha and beta which I have been talking about. So in this case, if you see the black one, so there would be some, if you draw, and the alpha value is somewhere here, beta value is somewhere here, if you draw the vertical, so the vertical point basically cuts these two graphs at two different places. The black one, which is more discriminating, is basically being cut by the vertical line at a certain point where the probability of accepting that lot is totally different from the case where the actual vertical line basically intersects or cuts the red line. Similarly, when you are going on to the right hand side and trying to find out the values of defects based on the value of beta, so obviously the intersection of the horizontal red line which I have now drawn, let me change the color, it will be much better for us to discriminate. So where they intersect, the black one and the red one, the level of lot quality fraction and defect and the corresponding probability of acceptance would definitely be much more discriminating for the black one, because their levels of beta and alphas, even if they are fixed or even if they are different, there would be higher propensity of accepting bad lots, or there would be high propensity of rejecting good lots. So obviously the graphs would make you well aware that whether they are too discriminating or less discriminating as per the general concept. Now the OC curves calculations have to be done, but technically in any statistical process control book, we will have the details of the calculations of the OC curves given based on the values of capital N, small n and C, but we will try to basically recap that and try to understand how they can be utilized. So the OC curve calculations in this case is the probability of observing exactly D defects is to be mentioned. So then the probability of accepting is simply the probability that D is less than some probability of defects which is given. So what I need to find out, if you pay attention to this, the probability distribution function, which is the PMF, because PMF would be the case for the discrete case. So there would be two slots, one is defective lots and one is non-defective lots. So the total lot you are picking up is N. So obviously the total number of defects and non-defectives would be such that it will give you a picture that in what different combinations you have those lots. So one would be D factorial D, one would be N minus factorial D, because you are basically dividing into two lots. So that D can be any one out of those lots which you are picking up. And obviously the probabilities are picking up, considering the picking up the lot good or picking up the observations as good as P, then obviously 1 minus P would be the probability of picking up the bad item, or vice versa, depending on however way you have basically explained the overall problem. So P can be good or P can be bad. So if P is good, then 1 minus P would be bad, or vice versa, depending, as I said, that how the framework of the problem has been done. So in this case, if I want to find out the number of defects, D being less than equal to C or greater than C, and depending on that whether we will basically accept or reject. So if D is less than C, obviously if you have made the plan, you will accept that particular lot. If D is greater than C, you will basically reject that lot. So in this case, what we need to find out is the total probability of the sum of the probabilities. So depending on the distribution function which is there in front of you, you will find out all the values of D's. So D's are the number of defects. So if the defects are 1 and if C is basically 3, so you will find out the probability for all the number of defects which are happening once. If defect is 2 in number, so obviously you will basically accept the lot whether D is 1 or D is 2. So obviously you will sum up all the probabilities for the values of D as 1 or 2. In case, say for example, if C is 5 and the number of defects is 4, so obviously it would mean that you find out the probabilities for all values of D when D is 0, when D is 1, when D is 2, when D is 3 and D is 4. because then in that on all these instances you are accepting that lot. So, hence you have to find out the probability depending on the sum of all the different type of scenarios which are there in front of you. For example, if the lot fraction defective is given as p is 0.1, then the lot fraction not defective would be 1 minus p. So, now if n is given as 89, c is 2, then obviously if d is 0 you will accept, d is 1 you will accept, and d is 2 also you will accept, but in the case if d is more than 2 you will reject that. So, if you are trying to find out the probability PA, it will be given by the summation on all the probabilities, that value comes out to be about 93 for 97, which means the PA value, which is the overall concept of how you will accept that lot, would be given that out of a lot of a size of 100 or doing that experiment 100 number of times, there would be a propensity that you accept it about 94 number of times. 93.97 is almost 94, that is why I said 94 number of times. Now, as I mentioned that the operating characteristic curve depends on capital N, small n, c, the type of distribution, so on and so forth. So, here in the figures which are figure 15.3, 15.4 and 15.5, which all have been taken from the book by Montgomery, you will understand how the overall discussion changes. So, if you consider the ideal operating characteristic curve, it will basically be a vertical line. So, vertical line, which I mean is basically depending on the, so the vertical line gives you the case that what is the value of alpha and beta, that can be found out. So, if alpha and beta are given, from here you will know that the lot size acceptance and lot size defects depend on alpha and values, and beta values would be accordingly. So, obviously it would mean that wherever the values of verticals are, they will always cut intersect the horizontal line at a particular point. So, this probability of acceptance or dejections basically remains the same. Again, if you are going in the horizontal direction, they will basically give you the value depending on what the beta value is. It will you will understand that acceptance and dejection would be at the same level. Now, when we are considering the operating characteristic curve for different sample size, so now what we are doing is that we have limited or made fixed the sample size small n and c are changing. As they keep changing, as I have drawn there about 3 or 4 slides away, if you measure PA along y axis, P along x axis, so these values of n and c would give you different types of curves. So, if you want to basically find out, given a beta value, what is the level of P and PA, you will again draw the horizontal and basically find out the intersection point based on which you will find out P. And if you are interested more with a given value of alpha, you will basically go vertical up, where they come here, because here they are too much concentrated, so you cannot basically see them, but there would be different levels of PA values, which will give you the probability of acceptance, and based on which you can take a decision. Now, if you basically understand that for a same sample size we are changing the C value, which is the level of accepting. So, if C is 10, C is 5, C is 4, again the graphs changes, but the graphs changes, the characteristic change of the graphs is totally different with respect to the case when you are changing both n and c. So, again in this case, if you find out beta and alpha accordingly, draw the horizontal, draw the vertical, they give you different level of points at which the probability of acceptance would be dictated depending on the value of n and different values of c, which we have considered for the third graph. So, again I am mentioning, for the second graph which is there, we are considering different values of n, different values of c. Here n is small n. In the third graph, we are considering small n to be fixed, but we are changing the value of c. Obviously, it will also happen that if you keep c fixed and change the value of n, you will have different curves also, but the general characteristics of the OC curves would remain the same. So, other aspects of OC curve behaviors would be OC curves for single sampling plan with C is equal to 0, that means you are only sampling 1. So, those curves which are given in front of you for different values of n as 50, 100 and 200 with different values of c are given. Again you are measuring PA along the y axis and P along the x axis. Now, let us come to the other type of graphs. All are the OC curves, but here what is important to note is that in many of the examples which I did mention, though fleetingly, that the main dictating parameters based on which the OC curves would be drawn are capital N, small n and small c. Now, till now we have only discussed the sample size small n and the number of defects which are there in the sample, and based on the number of defects which is now in actually is d, whether d is less than equal to c or greater than c, you accept or reject that particular lot. It may so happen that the population from where you are picking up may not be infinite. Technically, if it is infinite, obviously the problem is solved. So, but if they are not infinite, obviously that actual value of capital N should also come into the picture in order to dictate or give you the information that what are the values of PA and P, which will give you some information about the overall quality concept based on which you are trying to do the sampling plan. So, lot fraction defective P, then probability acceptance PA are all measured along the respective axis which are x and y. And in this curve we see that depending on a fixed value of C, a changing value of small n and a changing value of capital N, you will basically have different values of OC curves, and again those OC curves can be utilized to study the overall sampling plan which is there. So, just to mention, these capital N can also be changed, small n can also be changed, and C value can also be changed accordingly. Now, you want to basically concentrate on the concept of rectifying the inspection plan based on whether things are right or wrong. So, the rectifying inspection refers to the inspection programs when 100% inspections or screening of the rejected lots are which all have been discovered, those bad items have been discovered, are either removed or replaced with known good items. Consequently, average fraction defect in the stream of outgoing lots is lower than the fraction defective in the common lots, because those lots which are bad, I basically replace them, but obviously there would be some other observations also which are bad, which I have not been able to replace. So, if that is the case, when the lot after the replacement of the bad items which I have found out are replaced, when they go into the final inspection along the process, obviously the overall PA value and P value would change, because now the total quantum of such lots is less. So, what it happens is incoming lots fraction defect is given as P naught and inspection takes place. If rejected lots are there, obviously you will basically try to replace them. In accepted lots are there, the fraction defect remains continues to be PA, and the fraction defective, if the rejected lots are there, what you will do is replace them and continue along that. So, outgoing loss fraction defects P1 would be less than P0, and again if you follow this policy, again a different set of such flows would be there, where you will have a P2 value. So, P2 value would definitely be less than P1. But what is important to note is that all this inspection entails a cost, whether it is actually worthwhile to spend that amount of money in order to overcome the defect, that would be the main question which we will try to answer in the practical situation. So, with this I will end the 16th lecture and start with the 17th lecture, continuing the concept of AQL and OC curves and so on and so forth. Have a nice day. Thank you very much.